Hello, my name is Graeme Rocher. I'm an architect at Oracle Labs, where I work on Micronaut and GraalVM. Today, we're going to be doing a presentation on using Micronaut and GraalVM to build cloud portable applications that you can deploy to multiple clouds in a portable manner. So on the agenda today, we will do an introduction to the Micronaut framework. For those who haven't heard of it, we will do an introduction to GraalVM. We will do an introduction to building cloud-native applications with the two, and we will do an overview and an understanding how to build cloud-native applications that remain portable and address the challenges of cloud portability and vendor lock-in. And we'll do some demos, so we should have some fun. In terms of an introduction to Micronaut, the Micronaut framework is an open source Java framework that's focused largely on modern architectures like serverless and microservices, in that it lets you build those types of applications, but it's also a general purpose application framework for building any kind of application using Java. It features a dependency injection programming model based on annotations, which is very familiar to a lot of developers who are accustomed to things like Spring or CDI, where you can use annotations to define how your applications work, and the application is then wired together. And this kind of model is really great for cloud applications, as we'll see during the course of this presentation. Micronaut works slightly differently to other frameworks out there on the market in that it works through the use of annotation processes, which essentially allows it to plug into the Java compiler and do a lot more work during the compilation phase of your application, thus eliminating the need for a lot of the traditionally dynamic features in Java. So Micronaut doesn't need to use things like reflection, dynamic class loading, runtime generated proxies that traditional frameworks like Spring do, because everything is done and computed ahead of time during the compilation of the application. The net result of this is that the Micronaut runtime is significantly smaller and more efficient. And in terms of the HTTP layer, it has a client and server based on the asynchronous netty IO toolkit. And the goal of Micronaut is to improve developer productivity when building cloud applications, deployable to multiple clouds. If you want to find out more, you can go to micronaut.io, the website, main website for Micronaut, and you can find the source code for Micronaut, which is Apache licensed, available on GitHub at the link below. For those of you who haven't heard of GraalVM, GraalVM is a relatively new virtual machine out of Oracle Labs that is most famous for its ability to compute Java applications into self-contained native binaries. These are great for cloud deployments. The reason being, you can build a much smaller native executable that is targeted for the particular containerized environment. It's very typical in cloud applications to deploy to containers, specifically, in particular, if you're deploying to things like Kubernetes. With GraalVM, you can build native executables that target Linux. These containers significantly reduce the amount of memory required and improve startup time of your application, which means if you're building serverless applications, it resolves a lot of the cold start concerns a lot of folks would have with serverless, and even for microservices where you need your containers to be coming up and down and auto-scaling very quickly based on the demand for your application. These kinds of containerized workloads are ideal for GraalVM. You can find more about GraalVM at graalvm.org, and you can access the GitHub repository at github.com/GraalVM, and there's some demos there that you can try out. So how do these two technologies relate to each other? Well, the two, Micronaut framework and GraalVM, are more or less a match made in heaven. The reason is because GraalVM, if your Java application needs to do any kind of reflection, runtime proxies, bytecode generation, dynamic class loading, All of these features are supported by GraalVM's native image tool. However, they require configuration ahead of time. And since Micronaut doesn't do any of these things, it allows GraalVM to perform the closed world static analysis that it's able to completely analyze in a closed world manner your application and compute a native executable without requiring actually much, if any, additional configuration for the application. And once you've computed a Micronaut framework application into a native executable with GraalVM, the startup time is orders of magnitude faster. And for a simple application, the memory consumption is dramatically reduced, often a third of what is required for running the full Java virtual machine. So they're an exciting combination of technologies and great when used in combination. And users are enjoying this combination of Micronaut framework and GraalVM. So let's now talk about what does it mean for an application to be cloud native. So in general, when we talk about cloud native, it's about adhering to the principles of 12-factor applications. There's a lot of information on 12-factor, but one of the key ones is to separate configuration from the application to avoid coupling to the environment. So what does that mean? So essentially, you don't want to hard code within the code of your application the fact that you're running on a particular execution environment, whether it be a particular cloud vendor or a particular configuration in bare metal deployments. You really don't want to hard code that fact into the application itself. When you do deploy to the cloud, you should use abstractions and interfaces where appropriate to avoid coupling to the cloud and maintain your application's ability to be portable across deployments. 12 factors also, a lot about maximizing observability of your application. It's critical in cloud observability, traceability, metrics, understanding the performance of your application, the need to scale up and down. Observability becomes key in cloud native deployments, and as is the requirement to automate deployments and releases through, for example, DevOps pipelines and so on and so forth. So, it's bringing this cloud awareness, this cloud nativeness to your application, which has a massive influence on how you design your application. So the Micronaut framework has a lot of abstractions already built in and a programming model that encourages your application to be and remain portable across different cloud environments. First of all is the programming model, which is based on dependency injection and inversion of control. This kind of loose coupling between components that dependency injection promotes allows your components within your application to be easily swapped out and changed at runtime, and thus allowing the level of customizability needed that is often required when you move from one cloud to another. It also has integrated ability to adapt your application to the running cloud environment by detecting which environment you're actually running on. This is really useful if you need to, for example, activate certain components only on a particular cloud environment. And it has integrated abstractions for major cloud services. So if you think about different cloud services like object storage, email, streaming, logging, the clouds often provide the services to your application for all of these different characteristics. For example, if you want to trace your application or provide metrics or read secrets or authenticate via OpenID Connect, all of these are provided by your cloud platform, and you really don't want to couple your application directly to these cloud services of a particular vendor if your ultimate goal is for your application to be portable across clouds. So, so these all lead to, in general, cloud challenges to avoid lock-in to particular clouds, because each public cloud, if you look at AWS or Oracle Cloud or Google Cloud, has distinct APIs to interact with these services, from object storage to pub/sub messaging. And if you look at where we come from in the Java ecosystem, where there's been a kind of effort to standardize these things within the Jakarta EE and containers and so forth, where there were standards on the Java side for making sure applications were deployable across Jakarta EE containers. We're now living in a completely new world where the containers are now the clouds, and new abstractions are needed to ensure these your applications remain portable across cloud vendors. Because ultimately, once you start with using cloud-specific APIs, it's very difficult to then move to another cloud provider in the future as your requirements evolve, or you may even want to deploy to multiple cloud vendors simultaneously, taking advantage of cloud resources and cloud data centers in different regions and around the world that may have more availability or less availability or better pricing. A lot of companies deploy to multiple clouds and use that to their advantage. So avoiding vendor lock-in when you build your application is key. So I'm going to show you a demo of exactly how to do that with Micronaut and to build so-called GraalVM cloud-native applications that are ready to be turned into GraalVM native executables and are already ready to be deployed across multiple clouds. So I have a sample application here that's structured into a multi-project build. So we have a app directory where which contains my main application source code. And this application is a pretty simple Micronaut Java application where we have a Java directory. There's an application class, which is like the main entry point for my application, which I can run directly from my browser here. We have a entity, which is mapped to a relational database, which represents a table and rows within the database. We have a repository using Micronaut data, which performs CRUD operations using a in-memory database by default. And it's able to read and write objects from the database. And we have a controller, which provides a set of endpoints by default mapped to the /people URI, which uses the repository to implement functionality, for example, listing all the people in the application, finding a particular person by ID, and in addition, retrieving an image for a particular person by their ID using one of the cloud abstractions that Micronaut has called object storage operations. So this is an example. The io.micronaut object storage operations interface is an example of an abstraction over the different cloud providers, where there's not, I'm not referencing directly here AWS or Oracle Cloud implementation details. And in fact, by default for my application, I have provided an implementation of this interface as another component that is activated if no other components are present. That just uses the class path of my application to read images from the class path of my application. So it's going to read the images from this directory. So the net result of this is I can run this application locally because there's no coupling to the cloud. It starts up, it's using an in-memory database. And I can visit the application and we can come in here and list all the people. It's using an in-memory database. And I can click on a person, I can see an image loaded from disk over here. And it all works completely disconnected from the cloud. Obviously, it's a very simple application, just listing some people and reading some images for a particular person. But the key here is that it's completely decoupled from the actual cloud. There's no actual cloud references here. I'm not using cloud APIs. I'm not using anything specific. I have a configuration for my development environment that uses an in-memory database, but there's nothing cloud specific here being used in my application. And this has benefits because I can come in to my tests, and I have a number of tests here. I have a test which is going to test listing all the people, and I can run my tests locally, and I can feel productive that my tests work locally. I'm not depending on cloud resources to write my tests. I can test the functionality of my application, and it all is well. It's completely decoupled from the cloud. It has a couple of views here, which I didn't mention, that are, it's just renders on HTML pages. But it's a pretty simple application that does a bit of database access, a bit of object storage, but nothing directly dependent on the cloud. Then in each, I have two additional sub-projects, one called AWS and one called OCI. The AWS one, the only thing it does, in addition, is essentially it depends on my core application. It depends on this core application, excluding the in-memory database, and it adds additional dependencies that integrate my application with the cloud. It adds the AWS SDK. It adds metrics export using CloudWatch. It adds tracing using AWS X-Ray. It adds object storage using AWS and S3. It reads all of the configuration from my application from secrets defined by AWS Secret Manager. And it uses MySQL in production using Amazon RDS. So all of this is just defining additional dependencies that customize the application for the cloud environment. So additional dependencies and additional configuration. So if we look in source main resources here, we have first of all, let's look at the main directory, the main class. We have a source main Java directory with an AWS application, and that activates the fact that this application is going to run on Amazon. It's going to target the Amazon EC2 environment. This in turn triggers the fact that the application is going to load additional configuration that is specific to that environment. So it'll bootstrap and enable secrets via AWS Secret Manager. It will be configured to use object storage via S3. It will be configured to export metrics to CloudWatch. It will be configured to use AWS RDS for database access and MySQL. And it will be configured to export traces to CloudWatch tracing. So I can run this application. And once again, it's completely decoupled from the cloud. The actual application. Oops, I think first of all, I needed to stop the other application. Let me stop that again. Oops. Let's run this again. Okay, so I'm running it again, and you can see that it's established the environment is EC2. It's connecting up to my Amazon RDS database, and the application has been completely reconfigured to allow deployment to the cloud and also allow observability. So we can click on this, and it's essentially the same application, right? It's the exact same application, except it's loading the images from S3 buckets instead of locally from disk, and it's using an Amazon RDS instance. And the great thing is we get all that insight. If we go to, for example, CloudWatch, we get all the insight from Amazon Cloud and the observability of seeing trace information coming from my application into the cloud, where the application is being traced, and we'll get metrics, we'll get traces, because of the fact that we've activated those services through additional configuration in my application by sending traces to X-Ray. And the same thing is possible with Oracle Cloud. So we have another subproject here. Again, the only difference here is we have additional build configuration that depends on my core application where all the functionality is implemented. It excludes the H2 module, so the in-memory database. It adds tracing via Zipkin. It adds metrics via Oracle Cloud Application Monitoring. It adds object storage via Oracle Cloud Object Storage. It adds integration with Oracle Cloud Autonomous Transaction Processing just by defining a few additional dependencies. Integration with the Oracle Cloud SDK. And all of the secrets to configure the application are read from Oracle Cloud Vault. So the actual configuration, again, is slightly different for the application. We have here a bootstrap Oracle Cloud.yaml, which specifies which vault to read all the secrets from. And we have specific configuration to point to a particular Oracle Cloud object storage bucket to store and read my images. Metrics are exported to Oracle Cloud Monitoring. An ATP instance is used for database. So we have an Oracle database instance being used in this case. And trace information is being sent to Oracle Cloud Application Performance Monitoring, with the secrets being provided through Oracle Cloud Vault for all of this configuration. So all of these placeholders are being populated by secrets, so I never have to hard code in an insecure manner configuration into my application. That all comes in via Oracle Cloud Vault. And we can run this application the same way, right? So we can run it. And in this case, it's going to be configured completely to use all the Oracle Cloud services instead of the Amazon services. So my application is completely cloud portable. There's no direct coupling in any of my application code to either of these clouds. I simply provide additional configuration and additional dependencies, and my application can be portably moved from one cloud to another. In addition, I can build either of these applications into native images using Graal VM native image, which can produce a native executable, which I can run and benefit from the characteristics of native image, which in terms of dramatically improved startup time and memory consumption of my application. So startup time was halved, and if we looked at the AWS process in memory, memory consumption is only 70 megabyte. So dramatic improvement in memory consumption and by converting into a native executable. So that is essentially the demo application. All of this source code will be made available as part of this presentation, and you can see there are instructions in the README on how to set up this application to use distinct cloud services, where the code is completely separated from the cloud environment itself, and you can portably move the application from one cloud to the other just through configuring different cloud services and modifying your build configuration to pull in different dependencies. And the big advantage of this as well is that, of structuring your application in this manner is the fact that, to deploy to AWS, I don't have to include Oracle Cloud dependencies, or to deploy to Oracle Cloud, I don't have to include AWS dependencies that just bloat your application's dependency graph even further. You can structure your app in a logical manner where you have cloud-specific modules. When you're actually going to deploy, you can build either of the applications into, for example, the Oracle Cloud one, into a Docker image, and push that up into, for example, Oracle Cloud Container Registry or the AWS equivalent. Push the app and deploy with instance principles that allow access to all the resources required in the cloud. So that's the demo. So some cloud portability tips then. Use multi-project builds with a unique sub-project per cloud to avoid bloating your application's dependencies with different cloud SDKs. That's key to keeping your application's dependency graph small and basically eliminating the possibility of conflicts. You should program to interfaces. Use interfaces in Java to ensure loose coupling, and dependency injection systems like Micronaut, which allow to avoid the hard coding of logic that couples you to a particular cloud, to a particular environment, makes your applications more pluggable, more extensible, more adaptable to the cloud environment. You should activate specific environments or use environment detection if possible, but activate specific environments so that you're writing components that are only available in a certain cloud. That's one thing that I perhaps didn't show, but basically, for example, with the AWS module here, it activated the EC2 environment. And because we're using MySQL in EC2, and the original repository was targeting the H2 database, we actually define an extension to that that uses MySQL and replaces the component within my application only when running in EC2. So these kind of annotations that allow you to replace components in your application is the real advantage of Micronaut and a dependency injection system, where you can basically replace components for a particular cloud environment, which is key. And you should use containerized testing tools like test containers or emulators for writing integration tests for each cloud. So, for example, on AWS, you could use local stack. GCP, you could use the emulators. As much as possible, ensure a high level of testing as much as possible. And of course, mocking and using local versions of, in the cases where you cannot test against real cloud resources. So to get started, you can create an application with Micronaut at start.micronaut.io. You can use whichever IDE you prefer. Micronaut has great support for IntelliJ and VS Code IDEs. You can check out the documentation at docs.micronaut.io. There are a lot of guides on multi-cloud topics at guides.micronaut.io, so do check those out. To learn about GraalVM, check out the documentation at graalvm.org. And to grab the sample code for this presentation, head over to that repository right there at the bottom. So in summary, the Micronaut framework provides modules to effectively build cloud portable applications. With GraalVM native image, it's able to further optimize those applications for more efficient cloud deployment using the native image tool. You can build cloud portable applications if you correctly structure your application and use decoupled architectures, dependency injection frameworks like Micronaut, and design your applications specifically with cloud portability in mind. Thank you very much. I hope you enjoyed this presentation and enjoy the rest of the event.